My name's Stephen Kell from King's College London. I'll be chairing this session. We have three talks, okay. And the first is Matěj from Charles University talking about copy and patch compilation for R. Take it away, Matěj.
Okay, thank you. Hi, my name is Matěj, and I will be talking about the copy and patch JIT compilation for R. So to start off, let me tell you why I'm here. If you've been at this track last year, you have seen a keynote from Brent Booker on CPython's runtime. One of the major things he talked about was implementing a copy and patch JIT compiler for Python. This inspired the topic of my thesis, in which I implemented the same method of JIT compilation for the R programming language. What I want to show you today is an experience report on how the copy and patch works in the context of R. For those that are not familiar with R, it is a programming language used by statisticians and is mainly designed for intuitive use, even for people from outside of computer science. It is interpreted, dynamically typed, and generally supports a lot of high-level concepts, notably, for example, the read-write access to the call stack via extensive reflection. While powerful, these language features also make it quite slow. And not just slower than C, what I mean is much slower than Python, kind of slow. This also makes it hard to optimize and compile to native code. Now a quick refresher about the copy and patch itself. It is a method for constructing baseline JITs, with its main features being very fast compilation and minimal work for both development and maintenance compared to full-fledged JIT compilers. It was introduced by Horan Shu at Uppsala 2021, and Horan implemented it for Lua, and he was later followed by Brent, who implemented it for Python, and his contribution is now part of the official CPython distribution. Let's see a quick demo of how copy and patch works. Assume we have a simple toy language and the following statement that you see. Let's also say that this language can be compiled to a stack-based bytecode. As such. To run this bytecode, we create a simple interpreter loop. The semantics of the bytecode are straightforward. The ldconst pushes the compile time constant to stack, the add instruction pops two values from the stack and pushes back the result, and the return instruction pops a value from the stack and returns it from the function. But now comes the core idea for building a JIT using the copy and patch approach. Filtering out the interpreter stuff, we are left with the meat of the instructions. Now we can wrap each of these chunks of code into individual functions. Later, we want to chain these together by returning with a call to the next one, but as we don't know which one will be right now, we put a placeholder in its stead. So the last thing we need to change here is to make these instructions truly standalone, is to also make the constant in the ldconst stencil a placeholder, like so. These placeholders are designed as external global variables and external functions. Now that we have these standalone instructions, we can run an optimizing ahead-of-time compiler, which emits native code for each function. It is not important to understand the machine code here, but it's important to notice the compiled placeholders, which you can see highlighted in the output. In the context of copy and patch, these are called holes, and they will later be patched with actual data. Now, however, since the returning calls were optimized using take-call optimization to simple jumps, we can remove them altogether, leaving us with just the logic of the functions themselves. These chunks of code are then exported into header file, noting the locations of holes in them to later be patched. Combining all of this together gives us something that we call a stencil library. This will be used in the copy and patch run and will be loaded at runtime. And now let's see how the actual run of the copy and patch happens during the runtime. All of what we've seen so far been at the compile time, but now it's the runtime itself. So again, we have the same statement, and we first compile it with the bytecode compiler, the same as before. Now the stencil library is loaded into memory, and the copy and patch proceeds. So the first thing it does, it iterates over these instructions. And each time that it finds instruction from the stencil library, it emits the executable code into the memory where it wants to JIT it into. After this is extracted and emitted, we want to specialize this for the constant that is here. So instead of the placeholder, we can now fill in the actual constant, and in this way make this instruction really do what we want to do. After the first operation, we also continue with the second one, which is very similar to the first one, with the only difference that this time we patch the value 2 instead of 1. Since these instructions run sequentially and the first one falls through to the second one, this actually starts to create an executable code that can work as a function, which we'll later see. So we continue in the same way to emit the code for the add instruction. This doesn't have any placeholders to replace any holes, and now we continue on to return, which again is simpler. So now that we have this, we actually, in memory, we actually can call this as a sort of function if we cast a pointer to it. And first we need to mark the memory executable, but after that, this can be called as a regular function, and it returns with the last instruction as such. Now, after showing how the copy and patch works as an idea, let's see how it can be used in R. What you now see is the ld_const instruction from the toy language. But with a few modifications, we get the real ld_const instructions from the R bytecode. To achieve this, we had to extract the implementation of the instruction from GNU R. This was not as trivial as in the toy language, because GNU R's bytecode implementation is tightly coupled with its runtime, so we sometimes had to do some modifications to make the instructions standalone. Here you can see our pipeline. So at build time, we extracted the standalone instructions, and at build time, we generate the stencils from them, as you've seen on the toy language, similar to that. We are left with the stencil library, and now to jump to runtime. So when we want to compile our function, first it's compiled to bytecode using GNU R. And then using the bytecode and the stencil library, we use the copy and patch, as we've seen, to emit native code. Here you can see a list of some optimizations that we did. I'll focus on the last three, which might be the most interesting from a technical standpoint. First, let's discuss the specialization of the ld_const stencil. Since the R language is dynamically typed, the constant can be of any type, and the implementation has to decide during runtime which to load, right? Well, actually not really. Since the constant is fully known at compile time, we also know its type. So the dynamic dispatch is completely unnecessary. It slows down the execution and bloats memory. To solve this, we can create stencils specifically for each dynamic type. By extracting the code for each of the class cases, we can create much smaller functions without the dynamic dispatch overhead. During the run of the copy and patch, we can choose which to use because we know what is the type of the used constant. Such optimization could be done even in an ahead-of-time compiler. But now let's move to similar optimizations, but one that actually utilizes the power of JIT compilation by using self-modifying code. The for loop in R is then using three instructions. Start for, which prepares the frame on the stack. Step for, which advances the iterator. And end for, clearing up the frame on the stack. On the right here, you can see an example R code and the bytecode that it compiles into. The ld_const first loads the constant to be iterated over on the stack, and the start for instruction initializes with it. Each iteration, the step for is called, and if the loop is not terminated, it jumps back to its body. After the terminating condition occurs, it just falls through to end the loop. So in these optimizations, we focused on the step for instruction. Same as the ld_const, even this instruction suffers from runtime type dispatch, and we can see here that this piece of code is how large the step for implementation is in the GNU R. It is made almost entirely from a single switch statement that chooses one of 10 possible variants to execute. This makes for the step 4 stencil to be unnecessarily large, suffering again from dynamic type dispatch. And since the value is iterated over, it is known during start 4, and this is again unnecessary. What's worse, it applies to each iteration of potentially millions of cycles. But this time, it cannot be solved by just choosing the right stencil at compile time, as it is yet unknown what will be on the stack at that point. We solve this again by extracting the individual variants into separate stencils, each the size it needs. But instead of at compile time, it is at runtime that the code is copied into place, self-modifying to fit the correct dynamic type. More specifically, the modification happens during the start for instruction, where it knows which type it should choose. Let's see a demo of this. So at compile time, during the copy and patch, native code like this is emitted into memory. The space in between start and N4 is left blank in the size of the largest step 4 variant. Now let's see the execution. So when the start 4 begins executing, it actually checks which of the types is there in the iterating variable, and it emits the right stencil into this code inside this memory that was left blank. After this, it also creates the jump from the step 4 until to the N4, so that it jumps over the space that was also left blank. And after this, it continues, and it continues onto the execution of the step 4 itself, which now doesn't have the dynamic dispatch, and it just uses what's needed for this actual type that we need. It iterates over and over until it is finished, and after that, it jumps at the end to end the for loop altogether. So to conclude this, all iterations of the loop use faster, specialized step 4 that we just showed. This makes for a better performance, especially in tight loop benchmarks. Such benchmarks showed 6% average improvement using this operation. Now, to talk about the last discussed optimizations, we must first address how relocations addressing works. Relocations are crucial for the copy and patch, as this is the method used to create holes in the stencils. So relocations on x86-64 can be, for our use case, simplified to 3 types. Absolute, which contain a full 64-bit address to the variable that we want to relocate. Relative to global offset table, which is now a 32-bit offset from the program counter to a lookup table where the address to the variable is stored. And a relative addressing, which is the relative offset from the program counter directly to the variable. Now, the relative addressing produces the most efficient instructions from these, but the problem with it is, of course, the memory offset has to fit in the 4-byte, 32-bit signed integer range. The problem we face is that we have to choose just one memory model to generate all of our stencils. It is possible that most of the relocations would fit in the fastest relative method, but there will be some that won't, preventing us from using it in general. Yes?
When you said the relative is faster, do you mean the relative instruction is small, or it's actually faster to execute?
It's both smaller and faster to execute, because it allows us to use more complex instructions on x86-64, which directly can address this. Okay. All right, so to solve this, we use a clever trick inspired by the CPython implementation that also tackled with this. The indirect relative method is chosen to compile the stencils. The instructions to access these relocations have 6 bytes, which is 2 for the instruction itself and 4 for the address. During the compilation phase of copy and patch, we detect whether a relocation is near enough in memory in a way it could potentially use the direct relative relocation. If so, we modify the native code. Since such instructions have 5 bytes, they fit inside the 6-byte space that was created by the compiler and can be directly replaced, with the last byte being replaced by a no-op. This works perfectly if the relocations point to a space near the executable. But this, however, does not always have to be the case, as the runtime, which is often called, can be anywhere in the memory. To help with this problem, we discovered a way how to make sure as many relocations as possible will be optimized. It works by scanning the Linux memory mappings for free space near the VM runtime and requesting this specific address from the mmap system call. This way, the code is JITted into a place we choose. In our testing, the relative addressing became possible for 82% of our locations, and the performance of using relative addressing versus absolute addressing improved by 9% across the board. It is important to note here that this could also be more difficult to port to other platforms, as they might not allow access to this sort of information, but this works on Linux. To conclude our efforts, we built a functional prototype able to compile any R function into native code. It took around 1,000 lines of code, changes in the GNU R virtual machine, which are almost exclusively just exposing symbols that should usually be hidden, to be able to use them for our JIT. The bytecode implementation took around 2,500 lines, being ported from the GNU R, and finally, the copy and patch engine itself is built around 1.2 thousand of C lines. The compiler is implemented as an R package, but at the moment requires the use of modified GNU R environment, as we've discussed with the exposed symbols. If GNU R decides to build an interface that compiles, this could hopefully change in the future, but it's not at the moment. The prototype we made at the moment also supports only the x86 64 Linux architecture. So to move on to evaluation, we evaluated based on 3 points: the performance of the code, the compilation size, and the compilation speed. And we evaluate this on 57 benchmarks in 4 suites. So first, the ME suite, which is a micro-benchmarking suite made of pathological cases of things that are usually slow in R. Then the RV-Fast suite made by Stefan Marr, who tests algorithmic benchmarks. The Shootout suite, also testing the algorithmic kind of programs, and Real Thing, which are the real-world R packages. And we tested using this configuration. So to see the performance graph, so the geomean speedup compared to GNU R is 1.26. And while this number is mostly driven by the micro benchmarks, as we've seen below, the real packages also show significant improvement of 1.23 times the performance of GNU R. It is important to know here that this performance benefit does not come just due to the use of copy and patch, but could be due to many differences how the stencils are extracted and compiled. So to move on to compilation size, we see that the stencils range from 6 bytes to almost 3 kilobytes. And the instructions in R are actually quite large, which compared to, for example, the CPython implementation could be a problem because it also results in quite big programs. And on average, each instruction has around 30 holes to patch. And to move on to compilation speed, we actually achieve 980 instructions per millisecond, which results to around 0.2 milliseconds per program on average. With such a speed, this allows for almost free recompilation and can therefore be used, for example, for feedback recording. To show something about the related work, as I've already discussed for the CPython, so this is different from our implementation in a way that the CPython compiles traces instead of functions, and they can directly reuse the instructions from their implementation. There was no need to extract it like we did, because the implementation in CPython can be used standalone as shown, and it supports all platforms and but the speed up that it achieves is just the same as it was before of 1.0. The reason for this is that the bytecode interpreter in CPython is already very optimal, and many optimizations before the JIT are before the JIT is even invoked, are already performed, which is not the case for R, which didn't receive as much love for the contributions. So in conclusion, we have successfully implemented the copy and patch for R, achieving the speedup of 1.26 compared to GNU R, and very fast compile times of just 0.2 milliseconds on average. As future work, we plan to integrate it as baseline JIT in a project focusing on creating new compiler infrastructure for R. Thank you.
Interesting. Okay, we have loads of time for questions. If anyone has a question, come up to the mic.
Is this on? Can you hear me? Is this on? Okay. Hello, Jeffrey Young from Epic Games.
Hey.
You report an average speed up of 1.26 times.
Yes.
But I'm curious to know what the median speed up is, or confidence bounds on that.
Oh, this is the geomean speed up that you see here. So,
Okay.
like these are all the benchmarks that we had. So
I see.
Yeah.
Yeah, and then can you go back to the dot plot?
To what? Sorry.
The scatter plot.
Oh, yeah. This is for the
yes.
compilation size.
I would be interested to see what just the baseline RJIT or is doing, just like the not your work, but I would like a comparison here with your work versus what was standard.
I see.
Yeah.
Well, here on the scatter plot we see the compilation size, which is, but like for here we are comparing to the GNU R actually.
Yeah, I would like to see the compilation size difference. Like I guess you said it's 6 bytes to 3 kilobytes, but I guess I'm just curious.
Bottom line is the number of bytecode. The R doesn't have a JIT.
Yeah, the R doesn't have a JIT besides the bytecode
okay.
compiler.
I misunderstood.
This is really a horrible blow up of size.
Yes, because it's
1,000 bytecodes, you get 500 KB.
right. Yes, it's very fast. Okay, thank you.
My question is, I'm wondering if you handle the polymorphic dispatch over type situation. So like my understanding of from your talk is that you profile types by like self-modifying the bytecode, right? And for example, in the for loop case, I mean, the example, there's like for int or something like that. And I wonder if you handle cases where you have seen two types in the same instruction, or do you just support like single type and then go back to dynamic dispatch if you see multiple types in the same place?
So we create all the stencils that are for all the types. So there are like 10 types,
right.
So we create 10 stencils, and there's always just one type in use during the for loop.
Sure.
So if it changes, the start for also like emits different stencil, like each time that the for loop starts. Is that what you are asking?
I'm not like specifically concerned about for loop. Like I'm wondering, like, is there a case where a single call site needs to support multiple types, like needs to have like support multiple dispatch targets from, for example, like are there method calls that need to handle different receiver types, or is it not a thing in R at all?
This is not the problem here. What I've shown that so these instructions always just use one type. When there are instructions that actually have to specialize multiple types, the dynamic dispatch is still kept in the instructions, because we cannot do anything about it for some instructions. But for those that we can, we did.
Right. So like you said, that will be going back to the dynamic dispatch instruction for supporting like the types you don't know of, or like, so like my question was more like, if you self-modify the bytecode to provide things, and if you, for example, the stencil have like a single type, specialized for a single type, then when there are cases, the single instruction needs to support a particular set of types, then you might, it's kind of harder with this approach to sort of specifically support for these set of types compared to like just doing the dynamic dispatch and then support everything. So like, is it the case, or like just not relevant to your like our language, I guess?
In there can always be just one. There's
okay.
no, yeah.
All right.
Okay.
Thank you.
In the case of the for loop and the early cons
So
that we've shown, it could be just one.
You're saying the for loop situation applies to everything else as well? Like,
No, it's like the for loop and the early cons that we've shown have always have just one, but the others sometimes they can have a lot of the types that they support, and we still need to include this. Like the dynamic dispatch is still in the instructions just for the for loop that we've shown.
right. So not for loop. Sorry then. So would you what would you do for other instructions that are not like for loop then?
Yeah, well, I guess we have to keep it in the stencil, the dynamic dispatch, because like if we cannot tell during the compilation which type will be there on the stack, we also cannot do anything about it.
We don't optimize.
Okay, all right, thank you.
Thank you for the great talk.
Thank you.
If I understand you correctly, when you are creating those stencils, you are putting the machine instructions directly, and you're not optimizing the final stencil, right?
Yes.
Did you explore applying like optimization, like instead of emitting instructions directly, translating to C, and then running it for optimizations to see if there's a better speed up?
I'm sorry, how?
Like by leveraging something like GCC, then you can maybe get better machine instructions, right?
Yeah. So you mean like emitting all of the code in C and then compiling it together to
Exactly.
executable? We have actually tried that.
And what were the results?
It was around the same actually. The
Interesting.
performance was around the same.
Okay, thank you very much.
Yeah. Thank you. Okay.
Well, so you had the problem where you want to make sure you could fit within the range of a 32-bit
Yes.
jump, and the solution was to be careful about the memory placement where you were putting your code. But what I didn't understand was what was your previous, because if your solution is we allocate memory in a special place such that we know we can stay within 4 gigabytes essentially, what were you doing previously that meant you could not be sure of that? Right. Were you just using malloc or something that could place it anywhere in the address space? Or
So if we cannot reach the instruction from where the code is jitted, we use the global offset table that we put very near the jitted code, so that it can reach this relatively, and then there it contains the.
But my question was, how did you end up in a situation where, because to me 4 gigabytes is quite a long way, right? So
Yeah.
how did you end up in a position where you could have things be spread about the address
Oh, I
space?
see. So like due to how the ASLR works in like the operating system, like it spreads the dynamic libraries across the memory. So it happens very often. Like for example, during the development, we noticed that the math library was being loaded somewhere else from the error runtime completely, and this forced us to do
So
this.
I think what I'd missed was that these are not just jumps from one piece of JIT code to another. These could be jumps to external library routines. Okay.
Yes.
So in that case, you still do have to worry about far jumps sometimes, but you sort of avoid them in the common
Yes.
case. Yeah. Cool. Got it. Thank you very much.
Thank you.
Do we have any final questions? We're still a little bit ahead of schedule, but we can also just move along to the next talk. If we don't. Okay, let's thank Matěj again. That's great.